Hello everyone, this is Professor Iris Miano giving you day 23 lecture video on section 7.1 again. We did present this section in the day 22 video, and for this first portion I'll be focusing just on the application style problems, and then after that we will introduce the law of signs for section 7.2. So in the lecture notes here, I have just copied and pasted all of the visual and formula items that were associated with the introduction to 7.1 in case it's relevant to some of the homework problems that you'll be working on, even the application ones. Mostly it's SOHCAHTOA and its reciprocal ratios that'll be relevant. Maybe not so much complementary angle theorem, but there it is just in case. Here's the Pythagorean theorem, and a reminder that the two other angles inside of your right triangle are complementary, which means that their measures sum to 90 degrees. And here again is a visual definition of angle of elevation and angle of depression. So that all being said, let's just dive into some more application-y examples. These first two are just straight up geometry problems, so not so much in the way of actual real-world context to it, but I just want to give us a chance to get a little bit warmed up on this material again before we get too deep into applications. So let's go ahead and look at number 46 here, in which a right triangle is described that has a hypotenuse of 10 centimeters. If one angle is 40 degrees, find the length of each leg. Okay, so the thing that we should do here is start things off with a drawing. Okay, so I'm just going to have a very rough drawing here of a right triangle. Here we go. There's a little box there indicating the location of the right angle. And what do we know about this triangle? Well, its hypotenuse is 10 centimeters, so we can go ahead and label the longest side, or, said another way, the side opposite the right angle is always the hypotenuse. And furthermore, one of the angles is 40 degrees. So let's say it's this one right here. Cool. So I'll put a little angle in there, a little arc, and put 40 degrees inside there. So this is all that we know about the triangle. And they're like, hey, come up with the lengths of each leg. So let's let this length be labeled length X and this other leg be labeled length Y, just to give it some kind of name there. Well, we want to tackle this. There's a couple of different ways that you can do it. What I would do right off the bat is recognize that knowing two of the three angle measures is enough information to get that last angle measurement. And so I'm going to use two arcs to indicate its measured label of 50 degrees. How do I know that it's 50 degrees? Because, as stated earlier, the two non-right angles in a right triangle have to be complementary. They have to sum to 90 degrees because the measure of all three angles added together for any triangle has to sum to 180 degrees total. So if 90 degrees is already allotted for that right angle, then there has to be 90 degrees left. Okay, so I'm going to use this this 40 degree angle in order to find the measure of the length X, okay? And the reason I'm going to do this is just stylistic choice. I'm going to use the sine. So one of the visuals that I was presented with when I was first learning triangle trig was SOHCAHTOA, and the SO looked like this. There was a big S and then an O over H ratio right next to it, which is just to say that the sine of an angle, and let's just say 40 degrees for now if I'm going to relate it to the length X, equals the ratio of the opposite side the x that I'm trying to solve for, over the hypotenuse, which is 10 centimeters, okay? So in order for me to calculate the value of x, I'm going to have to, well, I'll essentially be taking 10 times the sine of 40 degrees. So I'm going to have to use a calculator for this. I don't know the sine of 40 degrees off the top of my head. You're not supposed to know. That's not the point of this. The point of this is to be able to use a calculator. A scientific calculator will do, actually, for all of the trigonometric stuff that we have ahead. Scientific calculator should have a sine, cosine, tangent, and the inverse of each of those function buttons as well, which will definitely be coming in handy in this lecture. So let's go ahead and, for one thing, you want to make sure, if you have to use your calculator to calculate the sine, cosine, tangent, any of the trig function stuff, make sure you're in the correct mode. Now notice that we're dealing with these angle measures in degrees, right? So you'll want to check your mode, and depending on what kind of calculator you're using, it'll come about in various different ways, but make sure that your mode is in degrees. And mine is in degrees at the moment, so I'm going to take the sine of 40 degrees and then multiply that by a 10. And I should get 6.427876097, and then my calculator kind of cuts off right there. So if you are, so that equals x, which equals 6.427876097. Do you need to put all of this and then a ... as your final answer? No. I want to share with you the convention. If you're talking about a length, the length is supposed to be rounded to the nearest hundredth. So let's round this to the nearest hundredth, and it'll be 6.43, and then slap on the units if they are given, the units here being centimeters. Cool. Now let's do the same thing, only in order to calculate y, if you want to continue with the the opposite over hypotenuse ratio, we can do that. It's just change your angle to the 50-degree angle, because if you're trying to calculate y, the angle opposite of that is 50 degrees. So we can have a separate calculation in which we find the value of y by doing the sine of 50 degrees is equal to y over 10, which is, of course, multiplying both sides by 10. 10 times the sine of 50 degrees equaling y. Type that into your calculator, and you will get 7.66044444, whatever. But round it to the nearest hundredth, and you're good to go. In fact, you know what? I want to get into the habit of putting little squiggles, because we are estimating here. We're rounding to the nearest hundredth, which is not an exact calculation, but it's good enough for our purposes. Okay? So there you have it. There's your y value, and here's your x value approximated, and appropriate units are given. So that's that for your finding the lengths of each leg, which I, along the way, labeled as x and y. Okay. Great. Let's do one more kind of a warm-up-y kind of problem, and it has two parts to it. We are going to consider a right triangle that has an angle of a pi over 8 radian measure. Okay, so let's go ahead and draw ourselves a picture, and we'll do it under part A, which asks if one leg is of length 3 meters, what is the length of the hypotenuse? So let's get this basic information in the form of a picture. So let's say that this angle is pi over 8 radians. And notice that we're talking about radians instead of degrees. So if we're going to use our calculator at any point in getting through this problem, we need to change our mode to radians from, it's currently in degrees, right? If you were just following along with me for number 46. So we'll need to make sure you change the mode. I'll make it a little note here. Change mode from degrees to radians. I'll put an exclamation point at the end of it to really drive home the fact that this is important, okay? Now, to put more information on our right triangle, we need to determine which leg is the 3-meter leg in order to find the length of the hypotenuse. So this brings into question, well, am I saying, well, obviously this is the hypotenuse, right? And we're going to go ahead and label it of length x, just to give it a label, okay? But the 3 meters, does it go here? Or does it go here? I'm not sure, and there's not enough information in the prompt for part A to determine definitively where it should go in this particular scenario. So let's have two different cases. Case 1, let's entertain the case where pi over 8 is opposite the 3-meter leg. So pi over 8 angle is opposite the 3-meter leg. If this is the case, then we could set up the sine ratio. Sine of pi over 8 is opposite 3 over hypotenuse, right? So, Katoa. And we can go ahead and do a fun little algebraic bit of trickery here. Turns out, guys, watch this, that if you have your unknown in a denominator space in the ratio for any trig function, and the trig function is known, like, right, you want the unknown right here in the denominator to be the thing that you solve for, you can actually just pull a switcheroo. Watch this. Just switch them. And you'll find that algebraically this is the case. So x therefore equals 3 over the sine of pi over 8. Okay, so now reaching for your calculator, go ahead and type in 3 over, so division symbol, and you might want to put the sine of pi over 8 inside some parentheses just to make sure that the syntax goes really well. Again, changing your mode. I'm going to underline that in green so it really pops. And yes, I am serious about it. Change your mode to radians, and then type this in your calculator, and you should get that x is approximately, rounding it to, you know, 2 decimal places, and we're in meters right now. It's going to be 7.84 meters. That's case 1. Okay, but entertain case 2 now. What if the pi over 8 value is, the angle is adjacent to the 3-meter leg? So I'll just name this the pi over 8 angle is adjacent. So that's this scenario right here. What if 3 meters is right here? Adjacent to the 3-meter leg. Okay, well, if the known value is adjacent, I'll be going for the cosine ratio, wouldn't I? Cosine being adjacent over hypotenuse. So that'll be the cosine of pi over 8 is equal to 3 over x this time. Okay, but yeah, remember, do the algebraic bit of trickery there, do a little switcheroo and say, all right, that means that x has to equal 3 over the cosine of pi over 8. Carefully type this into your calculator, taking into account appropriate syntax, and you will get, in this case, x is approximately 3.25 meters. Again, round the value that you get in your calculator to the nearest hundredth and affix the appropriate units. So here are my 2 answers. So this leads me to part B, in which we ask, why are there 2 answers? How is this possible? Well, we're not sure, and I've kind of, I'm reiterating this now because the whole purpose of having these two cases addresses this question here. How is this possible? So I would say, and here's what I wrote in my notes, so I'll just copy that down. We're not certain if the pi over 8 radian angle is opposite or adjacent to the 3-meter leg. So we have to entertain both possibilities, yielding 2 answers. Hold on. Bill T's. There we go. There's my response in probably the worst possible handwriting. All right, let's get into some actual applications here. First one, directing a laser beam. Wow, very cool. Use the fact. Okay, sorry, let me read this to you. I'm reading my notes on accident. LOL. Directing a laser beam. The prompt says, a laser beam is to be directed through a small hole in the center of a circle of radius 10 feet. The origin of the beam is 35 feet from the circle. See the figure. At what angle of elevation should the beam be aimed to ensure that it goes through the hole? Okay. So in my notes, I say, let's use the fact that the radius of the disc or circle that's presented there in this kind of bluish gray color is also the length of the smaller leg right here, right? The other leg, so to speak. Okay, so we could say that this is a length of 10 feet as well. Okay. And let's also assume that the angle made from the origin of the beam, so this reddish line, orange line, what color is that? It's kind of orangish, and what's it called? The radius of that circle. Let's say that the angle formed here, we have to assume that it's a right angle, so I'm going to put a little box in that corner. So if that's the case, then we have this right triangle with legs of length 10 feet and 35 feet. So we can find the angle measure opposite the 10 foot or adjacent the 35 foot length in order to, answer the prompt here. Okay, so if we have the length opposite and the length adjacent, I'm thinking tangent ratio would be appropriate here. So that's your little TOA. Excuse me, hold on. That's T opposite over adjacent. That's like the kind of visual that I think of when I say the, made up word TOA to remember the ratio there. So that means if I'm going to go ahead and let x equal, right, this unknown angle here, then the tangent of x is going to equal 10 over 35, yeah? Opposite over adjacent. Cool. So we can reduce this 10/35 if we want to. It's not necessary, but I like to do it, just it's the algebraist inside of me, recognizing there's a common factor of 5, so it's really, I'm taking the tangent x of, the tangent of x is equal to 2/7. Let's go ahead and, rewrite this in terms of solving for x, so using a tangent inverse. You could think of it as taking the tangent inverse of both sides, or just saying, I'm going to unpack this by saying this is equivalent to x being equal to the tangent inverse of 2/7. Okay, so this tangent inverse is on pretty much every scientific calculator possible. It's the second function of the tangent button. So you know how you have that second button, which is, I don't know, oftentimes in blue, or it might be a yellow button or something like that. And more often than not, the upper left-hand corner of all the buttons that you have on your calculator, you want to press that first before you press the tangent, and that'll give you the tangent inverse, which is the second function associated with that tangent button. Okay, so typing that in, you shall get that, and you're going to get, hold on, let me just actually do this with my calculator, and I will give you the whole value that is given by my calculator. So we'll get that x equals 15.9453959, and then it goes on, but this is the extent of the calculator's output for me. So since x is a degree measurement, or it's an angle measurement, and happens to be in degrees, then I want to, hold on, yeah. So I want to, what's the word I'm looking for here? Oh, I wanted to introduce the convention associated with rounding degree measurements. So since the angle is in degrees, you're going to round to 1 decimal place, as opposed to if it's a length, you usually round to 2 decimal places and make sure that you have the units presented. Here, we're going to have 15.9 because that's the value that you'll get taking this number and rounding it to 1 decimal place, i.e. the tenths place. And don't forget your degree symbol, okay? And there you have it. So just as a little bit of recap in regard to the original context, the angle of elevation in order to have the laser beam go through the hole will be 15.9 degrees. Cool, and that's that. Now, it's all well and good when the exercise has a figure associated with it, but what if it doesn't? Well, number 62 is one such example, in which case it's going to be very important that we come up with a figure that matches what's being presented here, so that we know how to organize the information and answer the question. Okay, so the prompt states that we are finding the length of a mountain trail. A straight trail with an inclination of 17 degrees leads from a hotel at an elevation of 9,000 feet to a mountain lake at an elevation of 11,200 feet. What is the length of the trail? Okay, so here we go. So let's first draw a little picture here in which we have, let's say that this is a sea level right here where I'm starting my picture. And then we have this mountain that we're climbing, and let's say it's like the steady incline. That's supposed to be like the idea here. And so at 9,000 feet, there's this hotel, okay? So here is sea level. So essentially at 0 feet, 0 feet. And then up here at, let's say 9,000 feet is right here. 9,000 feet. We have the hotel. H for hotel, let's say. Okay, cool. Now, from here, there is a trail, right? And it goes up to a lake, a mountain lake, that's at 11,200 feet. This is the mountain lake. Okay, so what we're supposed to be gleaning from this is from the hotel to the mountain lake, there's this trail. So in this pink color, I'll say that this is the trail. Okay, trails in pink. So given that from the hotel to the mountain lake, there's a 17 degree inclination. So that's saying that there's like, you know, an assumed right angle here inside, and I'm inside of the mountain, mind you, but right here, we know that this level, this inclination measurement is 17 degrees at this point. Okay, so they're like, what is the length of the trail? So what's this, basically this hypotenuse of this right triangle that's in pink here, okay? Cool, so it would be really nice if we knew what this length was right here. And believe it or not, we can determine what that is because we have this whole length from here to here being 11,200, and then this length from underneath the triangle in question all the way to sea level being 9,000 feet. So if we subtract the 11,200 foot elevation at the mountain lake from the 9,000 elevation that's happening at the hotel, we'll get this height right here of 2,200 feet. So I'll go ahead and label that. Oops, hold on. Erase that right there. 2,200 feet. Just this distance from here to here. Cool. All right, so take that into account. The angle of elevation, and of course the hypotenuse of the pink triangle is going to be the trail distance that we want to grab. So we have opposite over hypotenuse. I'm thinking sine ratio is the way to go here. So setting up your sine ratio, you'll have the sine of 17 degrees is equal to 2,200. That's the opposite side over the hypotenuse, which is the trail. Let's go ahead and have this distance be T, capital T for trail, sure. Just for the sake of the ease of the, you know, algebraic bit, let's just go ahead and give it a single letter. And so switch these two, therefore T equals 2,200 divided by whatever the sine of 17 degrees is. Type that into your calculator very carefully and round to the nearest hundredth, and you'll get 7,524.67 feet. Okay? And it's perfectly fine for you to leave the value of the distance in feet. There's no need to turn it into miles. If you wanted to do so, that'd be fine. It's like, you know, a bit over a, yeah, I'm not even gonna entertain that. I didn't calculate for it. It's perfectly good to go to leave it in feet, and that's what the textbook expects you to do as well. Whatever the units are that are given, the appropriate units are also, you know, the same ones that are given. Unless, of course, they ask you specifically to give the length in a different unit. Okay, cool. Let's do one more of these, and then we're going to enter into law of sines. Very exciting, that next section. But let's do one more word problem together. Okay, we are estimating the width of the Mississippi River. A tourist at the top of the Gateway Arch, height 630 feet, in St. Louis, Missouri, observes a boat moored on the Illinois side of the Mississippi River, 2,070 feet directly across from the arch. Now, what does the word moored mean, you might wonder? I had to look it up myself because I wasn't quite sure. It just means that the boat is, you know, anchored or tied to some kind of post on the side in which it's mentioned. The Missouri side, I guess, was first mentioned. But this tourist also observes a boat moored on the Missouri side directly across from the first boat. See the diagram given at, or excuse me, yeah, see the diagram. So then given that B, the measure of angle B, that is cotangent inverse of 67 over 55, estimate the width of the Mississippi River at the St. Louis riverfront. Okay, so basically we're trying to find the distances between the, you know, endpoints of these boats right here, okay, which is, you know, the distance of the river at this particular part of the river. Okay, So what do we do here? The first thing that we need to do is pick apart this given information. It is really nice that they gave this to us, but what on earth do we do with it? Well, we want to come up with a way to calculate b off of this, and so like give it an actual value, so that if we knew what b was, we could, using the I think tangent would be most appropriate, figure out what at least the sum of a plus b is, and if we knew what b is, then we could subtract that and get the value of a. The tangent of a would give us right, opposite over adjacent, so that would give us this distance from the arch to the Missouri side boat, and then we could take that distance and subtract it from the total length from the arch to the Illinois side boat location. Okay, so that's going to be kind of our game plan, and it all starts with being able to calculate the value of b. Okay, so obviously they gave us b as the cotangent inverse, so I'll go ahead and write this down. B equals cotangent inverse of 67 over 55. Great. Now, use what you know about cotangent inverses, or inverse trigonometric functions, to rewrite this as a trigonometric function, namely the cotangent to begin with. So that means that the cotangent of b, excuse me, let me go ahead and erase this equal sign, sorry. Cotangent of b equals 67 over 55. Cool, cool, cool. All right. Well, I don't have a cotangent button on my calculator. Do you? I don't. And I certainly don't have a cotangent inverse button, so I wasn't able to just right off the bat to feed this into a calculator to find the value. But if I take this apart by, first defining it as a cotangent for some unknown angle, I can then take the reciprocal of both sides, and that'll give me the tangent of this unknown angle. Then I'm working with something that I can actually feed into my calculator. Okay, now I can tangent inverse both sides, or rewrite this in terms of the tangent inverse, and that'll give me my b in another form that I can actually type into my calculator. So here we go. Turns out b is equal to the tangent inverse of 55 over 67. And that's the trick. That's the bit of trickery. So now type that into your calculator, because remember, the tangent inverse is just going to be the second function on your tangent button in your scientific calculator. So you should get that b equals 39.38241941, and then it goes on forever, but this is the extent of the decimals that my calculator outputs to me. Now, why am I writing them all down? Because you're going to use this in a calculation that is going to get you to answer the question that's being presented here, okay, or to perform the estimation that they're asking about, okay? And the reason why you want to list as many decimal places as possible in the midst of the calculation is to reduce the amount of round-off error that you exhibit in your final answer. Because if you round too early, if I go around just using the b value as like 39.4 or something, round to the nearest tenth, I'm losing all of this other bits of information, okay? And if I do that, chances are, whatever my final answer is, it's going to be a little bit off of what the true final answer is if I had used at least more of the calculation. Like, yeah, we will round our final answers to the nearest hundredth if necessary, but don't do it too early, is all I'm saying. Okay, so if this is B, I'm just going to keep that in mind. Then what do I want to do with that? Oh, okay, so I want to then come up with a tangent ratio for a plus b. Okay, that's going to be my next move. Now, why do I want to do that? Because at least I can put the, considering this entire assumed to be right triangle, so that's like has to be assumed to be a right angle right here, in order for this all to work, I can do the opposite over adjacent to get at least the tangent of a plus b, and that's going to help me determine, using this value for b, an estimate of the value for a. Then I can find this distance right here, again by using a tangent ratio, subtract it from the 2,070 feet. Bob's your uncle, you got it. Okay, so again, here is my next move. I know that the tangent of a plus b is equal to 2,070 over 630. Remember, TOA, opposite over adjacent. Okay, you can cancel those out if you want to. And then you'll take the tangent inverse of both sides. So that means that a plus b will therefore equal tangent inverse of 207 over 63. Just reducing that fraction slightly by the factor of 10. Cool. And then here you'll get 73.0724869 That's the extent of what the calculator's giving me. Again, please take all of this information and use it as you go, okay? Don't round off early. Round off only at the end, okay? And I know some of you might be groaning at this, being like, oh, I have to write down all these numbers. Yeah, just write down the numbers. What does it take? A couple extra seconds? It's not that big of a deal, and the calculator's doing the heavy lifting here. Can you imagine trying to find this tangent inverse of this weird ratio by hand? Like, what? How would you even do that? Like, let's just be thankful that we have our calculators and that they're doing this for us, and not bemoan the fact that we're writing down a bunch of numbers with the decimal expansion. Okay, so if a plus b equals this, then that means that a is approximately equal to, now I'm going to take this number, this is a plus b, subtract the b, which is this 39.38, yes, the whole thing, and I'll get that a is about 33.69006753 ... That's fine. Like, this is a lot of significant figures. I'm in a good place here. So now take this number for a and then put it in a tangent ratio for a. So therefore the tangent of a equals, now let's go ahead and we need a dummy variable here. So the distance from the arch to the Missouri side boat, let's call it x. Okay, so I'm going to write on my little figure there and say the tangent of a, I'm not going to write this whole number down again, I'm just going to say a is about this number. Use it, of course, when you type it into your calculator, though, is equal to x, that value I'm trying to find, at least in the intermediate. It's not going to answer my question, but it's going to help me. Once I figure out what x is, I'm going to subtract that from 2070, and then I'll have the number that answers the prompt. Okay, so the ratio is opposite over adjacent, which is the 630. Okay, so really, I'm taking my 630, and I got to multiply it by the tangent of this number right here, the 33.69 blah, 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 aka value a, and that's x. Therefore, okay, so if you are taking as much information as you can and using this entire number, believe it or not, it's enough information for your calculator to spit out exactly 420 feet for x. Isn't that fun? Exactly. Okay, so that's just a consequence of your calculator getting enough significant figures to come up with this number. So cute. If x equals 420, then the distance that we're trying to grab here is the 2070 minus 420, which equals 1,650 feet. And that is your final answer. That is the width from width of the Mississippi River at that point. Okay? So I'll even label it width of Mississippi River. Mississippi River. Cool. Great. So, you know, those are the application problems that I have for this lecture. There are more. There are different ones. Let's go ahead and do whatever is helpful in class for more demonstrations if you'd like. But for the time being, let's shift gears over to the law of sines, which is now being introduced via section 7.2. So here's the story with the law of sines. 7.1 was all about triangle trig with right triangles, right? Okay. So that's all well and good if you happen to have right triangles, but there's not just right triangles in our lives. There are acute triangles, which we have in figure 18a right here. There are also obtuse triangles, which are in figure 18b and then also figure 19. So what do you do if you have those types of triangles and you still want to be able to complete the triangle or solve the triangle? Which means finding all of the interior angle measures and finding all of the side lengths, okay? Well, enter law of sines and law of cosines. So law of sines is going to take into account a couple of specific cases of acute and obtuse triangles, and obtuse, or said another way, oblique triangles, right, are going to be having this configuration of angle measures and corresponding opposite side lengths. So just to be clear here, angles capital A, B, and C will just be plopped down, wherever. And I know that angle C was always associated with the right angle for right triangles, but there's no such convention with like the biggest angle always being B or C or anything like that. It's more or less just like plop them down wherever in your generic figure when you're just trying to figure out who is where. And then the opposite side length will be the lowercase counterpart for whichever angle has been presented in the angle space already in the triangle. So for instance, notice that angle A, capital A, is right here. So the length opposite right here, like the length of the triangle in which A, if it had a light source, where would it be broadcasting its light? On the wall of length lowercase a. Furthermore, angle capital B broadcasts its light on opposite side lowercase b. Uppercase C angle broadcasts its light on opposite side lowercase c. So that's the convention, and we will definitely be labeling any triangles that we create to work with making some of these calculations in exactly the same way. Okay, so for law of sines, which is just basically a series of ratios of the sine of an angle and its corresponding opposite side length, we're going to be entertaining cases 1 and 2, okay? Cases 3 and 4 are associated with law of cosines, which will be discussed next time. So this is law of cosines. So to be continued on cases 3 and 4. Case 1 has a couple of different configurations in which one side and two angles are known. Okay, so that's could look like case 1 or case 2 if the side is between the two angles or not. Okay, so it could be an ASA or a SAA, SA, if you want. No, that's a ridiculous way to represent that acronym. But anyway, those are the two cases in which you can have two angles on a side. Cool. Case 2, we will have two sides and an angle. Okay, and the angle will not be included between the two sides, okay? So it's this SSA, and you may notice that it is spelling a particular, for some households, swear word spelled backwards. So it's definitely a tricky case. Now, when you're in your geometry class and you're trying to prove congruent triangles rather, this is not an acronym that you're able to use in order to prove that two triangles are congruent. So, something tricky is happening here. And it's definitely the case for implementing this law of sines. When you have two sides and a non-included angle, you definitely have this whole ambiguous case popping up. Okay, so we'll get into detail with that. So when you have this case 2 scenario, you can either have one possible triangle arise from it, two possible two possible triangles or none at all. So I'll go through with you the process by which I determine this, and it's not exactly what, I mean, it's, the way that I go through this process is not immediately connected to what the book presents as far as what to look out for. I don't know. I just see it my way as being a little bit different. Definitely connections can be drawn. Okay, in any event, here is law of sines. Here it is, finally, and it's just a string equivalence, right? As an equation, a three-part equation, in which we relate the ratio of the sine of an angle to its opposite side length. Okay, so that ratio holds true throughout the entire triangle. So every combination of a sine of an angle and its opposite side could be illustrated in a single, proportion, right? Like this is a string proportion, so to speak. There's three parts to it, but you could take any two ratios and set them equal to each other, and that's what you get in this box over here. Now, if you're interested in reading through the proof of the law of sines, you can look in your book on page 567. I'm not going to go into detail about that at all. Certainly, that'll become more relevant to you as you progress through your mathematical career. But for the time being, we're just going to work with law of sines. We're not going to be focusing at all on proving it or the proof itself. However, you are encouraged to read through the proof and try your best to, understand what it's saying to you. Furthermore, we want to remind ourselves that the interior angles of any triangle are always going to sum to 180 degrees. That's going to become very relevant to us in the exercises to come. So what we have presented here in this last collection of figures before we get into examples is basically the ambiguous case that arises when you're trying to solve, solving SSA triangles. Basically, you have all this stuff happening, okay? So there could be, like I said, no triangle at all. There could be one right triangle or one single triangle that's not necessarily right, okay? Or you could have two triangles, right? Didn't we have an instance earlier where we saw that there were two possible triangles happening in the previous section? Yeah, that's definitely possible with these SSA triangles. So when you're given two sides and a non-included angle, like there's three different things that could happen, okay? Well, four technically if you break the one triangle into the right triangle or, other triangle case, okay? So, definitely read through this bit. I took it from the textbook, but what I want to focus on is my process that I go through in determining if I have a one right triangle or one triangle, a no triangle, or two triangles situation, okay? So it's a step-by-step process, and you will perform the same steps every single time for every single example. So, and once you reach a particular kinds of snags, then you can either stop working because there will be like no possible triangle, or you'll know very clearly when there's two or when there's one. So here we go. Now we're not going to immediately do this SSA business. We're actually going to get warmed up a little bit and just solve a few triangles given a one of the first type of cases, okay? Case one scenario, not the case two ambiguous stuff just yet. Let's get warmed up. So notice for number 10, we're given it looks like it's an acute triangle. But yeah, it's considered to be oblique because it's not a right triangle. I guess is what needed to be stated earlier. So we need to find the values of lowercase a and lowercase b and capital C. So lowercase a and lowercase b are side lengths, right? And capital C is an interior angle measure. Let's start with capital C. That's going to be the easiest one to find, in which case we want to recognize that the interior angle sum of any triangle has to be 180 degrees. We know that one angle is 40 degrees, one angle is 45 degrees, and then C needs to be thrown in the mix, and the sum of them will be 180 degrees. Okay, so put your algebra hat on, and you'll be able to determine that C, therefore, has to equal 95 degrees. Okay, sum these together. What? 40 plus 45 is 85. Subtract from 180, you get 95 degrees. Okay, great. So that's one thing. See, done. One down, two to go. So let's go ahead and calculate next. We'll want to calculate the value of a lowercase a or lowercase b. We have enough information to do either one at this stage. In my notes, I'm looking at it, and I go for lowercase a first. So let's bust out the sign ratio. Relating what we know to be true, right? That we have the full information of the measure of angle C and its opposite side length. So start with that. The sine of, therefore, 95 degrees is in ratio with the 4 length right here because it's opposite. Set that equal to either the, you could go sine 45 degrees over A or sine 40 degrees over B. Doesn't matter. I'm going to go ahead and just do A first. Sine of 45 degrees, right? It's got to be opposite that A value. Go ahead and implement the cross product and solve for A, and you will get A equals 4 times the sine of 45 degrees over the sine of 95 degrees. I'm skipping a little bit of the algebra here, folks. So I'm going to go dot, 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 and then I just get there. Again, it's cross product, solve for A. So if I type this into my calculator, remember to be in degree mode. We're definitely working with degrees here. I'm going to get that A is approximately equal to, it's going to be some decimal, right? And round to the nearest hundredth because we're talking about a length. We don't have units here, but that's fine. We don't need them. It's going to be 2.84. Okay, so my calculator gave me much more than that as far as the decimal expansion is concerned, typing this into my calculator, but I'm rounding it to the nearest hundredth because that's the convention for side lengths. Okay, similarly, so that's A. This is A. Donezo. Let's go ahead and calculate B in a very similar way. The setup is, okay, and use, again, the thing you know very clearly, try not to use lowercase a even though you have it. It's just not as clean of a calculation. Rely on this full ratio of sine 95 degrees being associated with the length of 4 and put that in ratio with now the sine of 40 degrees. That's in ratio with the unknown b. Cross product, solve for b, therefore b equals 4 times the sine of 40 degrees over the sine of 95 degrees. Type that into your calculator very carefully, and you will get b is approximately 2.58. Okay, and there you have it. Let's do this one more time, but for a different triangle, and that is number 16. So I'm going to go ahead and put a little line there just to make sure it doesn't bleed over. Okay, cool. So again, we have 2 angle measurements out of the 3, so we can start there and give the value of C, 30 degrees plus 100 degrees plus whatever C is. That's got to sum to 180 degrees. So that means that C equals 50 degrees, if I'm not mistaken. Yep, there it goes. Okay, so again, please use the ratio that you already have complete with the sine of 30 degrees being over a value of 6, okay? Sine of 30 degrees over 6 is therefore equal to, pick one. Do you want to calculate A first or C first? Doesn't really matter. Let's go ahead and go for A. So that'll be equal to the sine of 100 degrees there over A. Okay, that's supposed to be a 6, not a B, just to be clear. So that's a 6. Cross product solve for A. A therefore equals 6 times the sine of 100 degrees all over the sine of 30 degrees. careful typing into your calculator will yield an A of approximately 11.82. Remember, always round to the nearest hundredth. Oh, we can box up our C as well. Okay, it's not much more to go. Let's maintain that sine of 30 degrees over 6 ratio and set it now equal to the sine of 50 degrees. So we can get the value of lowercase c. And cross product solve for c. So c, therefore, is equal to 6 times the sine of 50 degrees over the sine of 30 degrees. Oops, that's supposed to be sine 30 degrees. And therefore, c is approximately equal to 9.19. There you have it. Cool. All right, let's do one more. But this one, we're not going to be given the visual, so we got to come up with the visual. So it's our job to make sure that we are upholding this convention associated with where the side links are in relation to the angles that are established. So I think of it as like put down the angles first and then figure out where the side links are. It doesn't matter if you do it kind of the opposite way. Give yourself to begin with some generic triangle, and you know, you can make it have pointy edges here. I'm going to try that one more time. That was terrible. One more time. Boop, boop, boop. That's better. Okay. So I know it might look like a right triangle. That's unintentional. I'm going to go ahead and let C be like kind of the bigger, the more looking like it could be obtuse angle right there. And so therefore, since I established that C is going to be inside of the interior of this angle, the opposite side therefore needs to be the lowercase c, okay? B being 10 degrees, let's go ahead and say that this one is the 10-degree angle. That means that its opposite length right here has to be lowercase b, which I do have a value of 2 for, okay? Now I don't have the angle value of A. Uppercase A is for the angle, lowercase a is for the opposite side length. So that's the way that you should more or less be drawing your figure for number 22 where the figure isn't given. You gotta come up with it. Okay, so what do we do here? Well, the first thing we could do is find the value of uppercase A. That's easy. A plus 10 degrees plus 100 degrees is supposed to sum to 180 degrees. Therefore, A equals what? 70 degrees, if I'm not mistaken. Yep. Okay, and then we, go about this the same way that we did for the previous two examples. Set up a sine ratio for the ratio that you have all the information for. So which one do we have not only the degree measurement, but also the opposite side length, and that'll be for the B's. So therefore, sine of capital B, which is 10 degrees, is in ratio to lowercase b, which is 2. And set that equal to, well, which one do you want to calculate first, A or C? Doesn't matter. It looks like I did A first, so that'll be sine of 70 degrees over A. Okay, cross product solve for A, and you'll have A is equal to 2 times sine of 70 degrees over the sine of 10 degrees, which is approximately 10.82. Okay, similarly, let's go ahead and put a sine, the law of sines ratio going on with the known thing, sine of 10 degrees over 2 is equal to sine of 100 degrees over lowercase c. Cross product solve for c this time, therefore c equals 2 sine of 100 degrees over the sine of 10 degrees, and therefore c is equal to approximately 11.34. Cool. Done. So there, oh, I want this actually. A is 70 degrees, capital A that is, lowercase a is 10.82, Lowercase c is 11.34. Great. All right, let's get into some ambiguous case scenarios here. So in each of the next 3 exercises, we are going to have 2 sides and an angle given. It's our job to go through this particular process. So what I'm going to outline for you is the step-by-step process to determine if we have 1 triangle, 2 triangles, or no possible triangles. And whichever ones have resulting triangles or just a single triangle, we've got to solve them, okay? So there we have it. Cool. Let's exercise number 26 here, in which, where's that? There we go. Let me just get my notes here. Okay, so the first thing that I like to do is draw the triangle. I think that's the best way to move forward. So I'll just kind of put it off to the side here so I have plenty of room to do all of my calculations and get real generic with it. Okay, here we go. So what are we given? B is 40 degrees, and I decided for no reason in particular to put B right here, 40 degrees. So that means opposite B, capital B that is, I'll have the length lowercase b of 4. So wherever you decide to put the angle that you're given, if you have the length of the lowercase counterpart to that, you have to put it opposite that angle. That is so important to this, that you put things in the right places, okay? So after that, you could put the 3 length either here or here. It really doesn't matter at all. So I'll choose to put 3 here just so that it matches my notes, which means, because this is the length of lowercase c, that means that this angle opposite this length of 3 has to be uppercase c, and then that one means this one has to be uppercase a by, process of elimination. Therefore, this last remaining length has to be lowercase a. So that's a perfectly fine visual associated with this triangle that we're trying to solve, if possible. So we can use law of sines to find, I would go for the measure of angle C. Now, why would I do that? Well, that's the only way that you can really move forward here, because you have to use so you have one complete ratio, right? The sine of 40 degrees there over 4 is equal to either sine of C, uppercase C over lowercase c, or sine of uppercase a over lowercase a. Well, we have no information about either of the a's, but we have lowercase c. So we're going to use law of sines to find the measure of angle C, and this is how it's going to go, okay? Sine of C over 3 is equal to the sine of 40 degrees over 4. Okay, so use the cross product in order to solve for sine of C, okay? So when you do that, you get 4 times sine of C equals 3 times sine of 40, okay, and then divide both sides by 4. So therefore, dot, 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 you'll get sine of C equals 3/4, or 3 sine 40 over 4. I like to put the fraction as a coefficient on the sine 40. That's just my style. Okay, so algebraically, you'll solve for sine of C in this case. Now, I know what you're thinking. You're probably like, oh, I need to take the sine inverse of both sides, and then I could just find the value of C. Hold on a second, okay? You will want to check something first that's going to determine whether or not you should even proceed after this, okay? So just solve for the sine of C real quick. Go ahead and type in 3/4 times the sine of 40 degrees, and what do you get? Well, if you type that in, you will get that the sine of C is equal to 0.482090 7073. Were all of these values necessary? No. Actually, what you're really just looking for is you're trying to see if the sine of C is less than 1. Yes, it is. Yes, this number right here, less than 1, right? Some decimal that's less than 1, 0.48, blah, 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 blah. So then we may proceed. Okay, yes, proceed. Why do we care about this value being less than 1? Well, think of it this way. What's the sign ratio as far as side lengths are concerned? It's opposite over hypotenuse, right? If you're talking about a right triangle, which, you know, we're kind of trying to assume that this one isn't necessarily a right triangle, but that's something that we can kind of liken it to a little bit. So it's kind of like illustrating to us that the side lengths, if the sine of some angle was going to be greater than 1, then the lengths are going to be all wackadoo in such a way that they won't be able to close to form an actual triangle. Like, it'll be impossible for the lengths to actually line up to one another and connect at the vertices. Okay, so anyway, hopefully that makes sense. Not that we can really attribute it to an opposite over hypotenuse thing. We really can't, because that SOHCAHTOA stuff is just for right triangles. But that's the thing that I most draw from, is just to say, oh, well, you know, whatever was previously conceived as being the longest side, it actually wouldn't be anymore. Like, there just wouldn't be any way to connect the edges together. Okay, anyway. So you're looking for this value to be less than 1. If it is, yes, we can proceed. Okay, now take the sine inverse of both sides. So therefore C equals the sine inverse of 3/4 times the sine of 40 degrees. And what do you get? Well, for this, your calculator is going to give you 28.822. This is at least what my calculator gives me. 0.365 or 3.865. Okay, cool. So here's the second thing you want to be checking. Okay, with this value, you will actually call this C1. Yeah, I know. Subscripts are going to come into the mix here. Why? Because you want to check to see if there is a possibility of getting a C2. Now, what would the C2 be? The C2 would be the supplement of this, okay? Yes. So we want to entertain 2 different possible angles for C. Now, why do we need to do this? Because, guys, we are investigating the ambiguous case. There might be 2 triangles possible here. And if there are, this would be one of them, and C2 would be the supplement of this. So this is 180 degrees, and this is a degree measurement, okay? This is the possible value for C, is going to be 180 degrees minus C1. So what would that be? Well, that'll be approximately equal to, because I did this ahead of time, 151.2 and some change. 2 ... Okay, it turns out that we don't need that expansion here, and I'll tell you why. Consider this value as being the other possible C value. Well, if you added this to the 40 degrees that's already established, right, you'll notice that you get some value that's well beyond, right? Oh, excuse me. The 180 degrees that you know is the maximum number of angle, degrees possible inside of a triangle. So the fact that the supplement version of C added to the angle that's already established was well over 180 degrees, or any amount over 180 degrees, or even equal to it, right? Then you know that there is actually no possibility for a second triangle. So here, because of this, we know there's only one possible triangle. So this basically, earlier, the sine of C being less than 1 means that there's at least one triangle. So proceed at least one triangle ahead. This says that we know it's only one triangle. Only one triangle possible. You guys like my shorthand for triangle, just using the shape? Okay, so now let's go ahead and proceed. So C1, just call it C, okay? Then we can round this to the nearest, tenth of a degree for now. You'll want to use more of it in further calculations, but as far as being able to put the value down for a final answer, we are done calculating the value of C. It's 28.8 approximately. So we'll go ahead and box that up. But in order to calculate the value of A, we're going to need to take all of this number and subtract it from 180 and then also subtract 40. And therefore, you will get A equals, and I'm rounding it to the nearest tenth as well. Oh, and this is degrees, sorry, degrees. A is 111.2 degrees. Okay, and then we need to lastly find the value of capital A. So use the full known ratio associated with B's, okay? So we'll do the sine ratio for B's, which is sine of 40 degrees over 4 is equal to sine of A. Now I'm going to use the actual expansion of this, which I didn't write down, but I could tell you out loud that A is actually a rounded off version of 111.1779614 ... right? Okay, so I'm going to use that value in this calculation in order to get the value of A. So cross product solve for A, and you will get A is equal to 4 times the sine of capital A over sine of 40 degrees, which is approximately equal to 5.802, blah, 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 blah. Round that to the nearest hundredth. I know, in doing so, you're going to have a 0 at the end, but that is upholding the convention. A, therefore, is approximately equal to 5.80, okay? Cool. And that completes the triangle, or solves the triangle, so to speak. Because remember, we were given lowercase b, lowercase c, capital B, and we found capital A, capital C, and lowercase a. Those were the 3 remaining values that needed to get calculated, and we got them. Okay, just as a quick recap, we found the sine of the value of the angle that we were trying to calculate first, based on the information given, which in this case was C. We found it to be less than 1, which allowed us to proceed to determine if there was any triangles, right? If it was greater than 1, at that point we would have said no triangles possible. And since the supplement of the proposed value for C yielded an angle that would not be able to create a second triangle, we know that we only had 1 possible. Then we proceeded to finish solving the 1 triangle that we know is possible. Okay, great. Let's move on to number 32. Same process, okay? We're going to start by drawing a triangle. Let's go ahead and put the 70 degrees right here, 70 degrees there, and 70 degrees is capital A, so that means opposite that will be the length of 3. Then B, capital B, I'll put here, and therefore the opposite side will be 7 right there. And capital C will go here, and then lowercase c has to be the opposite side. Cool. This is one way that you can draw your, generic triangle visual here. Let's go ahead and create, using the sine ratio, the law of sines, to do the complete ratio of sine 70 degrees over 3. And let's set that equal to the ratio for B, because at least we know the side length of 7, and that'll allow us to calculate uppercase B, okay, over 7. So go ahead and do the cross product in order to solve for the sine of b. Before you get into any sine inverse stuff, just calculate sine of b, which will be 7/3 times the sine of 70 degrees. And what do you get? Well, you type this in your calculator, and you're going to notice you get 2.192616. Oh, wait, hold on. Who cares? This sine of b is greater than 1. Stop. No triangle possible. This will be an instance in which the side lengths that are already established and the non-included angle are in such a configuration that the side lengths will not be able to close on an actual triangle. Like the lengths will not be able to meet each other. Okay, so there is no triangle possible. We're just going to stop right there. Okay, so you will, in the very first calculation, be able to determine if there is no possible triangle, and it's by using the law of sines to determine your next step and stopping at figuring out if the sine of that angle is something greater than 1, because then you know you won't be able to have the triangle close on itself. Okay, cool. Now, so we've done one example in which we've had one possible triangle and we've had no possible triangle. You can probably guess through a process of elimination and context clues what's going to happen for this last one. And notice that I have the most amount of space provided. Spoiler alert, we're going to have 2 possible triangles for this one. So let's draw a generic figure in order to just move forward with this one. And so I'm going to put the known angle of 40 degrees right here, again for no particular reason other than that's what I have in my notes. The opposite side length, lowercase b, is given, so it goes here. C, let's say C is right here for, again, no particular reason. So therefore the opposite side length here has to be 5, and then A will be there, lowercase a here. Okay. So let's first set up the sine ratio that we know completely, which will be the sine of 40 degrees over 4 is equal to, well, what's the next sine ratio that we at least have half the information? That'll be for C. So sine of, hold on, sine of C, not just C. Sine of C is over 5. Okay. Cross product to solve for sine of C, because you want to check. I know, we know that it's going to be 2 triangles, it's going to work out, but let's do that check anyway, pretending that we don't know, which will say that sine of C is equal to 5/4 sine of 40 degrees. Oops, 5/4. Oops, 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 oops. Erase it. 5/4 sine of 40 degrees. And what do we get? 0.8034. Blah, 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 blah. Yes, the sine of C is less than 1. So we know it's a triangle, right? Cool. Proceed. All right, so now do your sine inverse of both sides. So you'll get C therefore equals sine inverse of 5/4 sine of 40 degrees. And this will at least give you your C1 value, okay? Which is what? 53.46414,901. Yeah, and it goes on forever, but you know, this is a good amount of significant figures. And yes, we're going to call this C1, and we're going to entertain the idea of there being a possible C2. And this is how you would do it, right? You take your 180 degrees, you take the supplement of this angle right here, okay? So, sorry, let me not actually write this whole thing down. Let's just use the fact that I already assigned it a value of C1. Let's also, sorry, make that 8 look a little prettier. 180 degrees minus C1, and this is degrees too, sure, okay? And that's going to equal 126.535.851. Okay, so dot, 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 right? So you want to know if I add the 40-degree angle that's already there, am I going to have any degrees left over to, have a third angle that can sum to 180 degrees? Well, yes, you will in this case. You have 166.5355851 dot, 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 and that is less than 180 degrees. So that means there's some degrees left over. So there is a possible value of C2. So the fact that this is less than 80 degrees tells you there's a second triangle. Cool. So let's investigate this C1 configuration. Okay, so and we'll associate this with a case 1. So C1, we can round this number to the nearest tenth now in order to just solidify a value, and that'll give me 35.5 degrees. Cool. I can even box it up. All done there. And then we want to get an A1, capital A1. So that'll be taking this number and subtracting it from 180, and then also subtracting that the 40 from it. And if you do that, you'll get an A1 value of, what do my notes say here? 86.5. Okay, so just to be clear, how did I get this number and get it so quickly? Well, I did the calculation ahead of time, LOL, but also it's just, you just need to determine what number, when added to 40 and 53.5, is going to sum to 180 degrees. And there you go, A1 will do it. Okay, so then we're going to take this A1 value and we're going to put it in a law of sines or ratio with the complete known ratio with the b's. Okay, so therefore, still in case 1, we're going to do sine of C1. Okay, yeah, you could do C1 or you could do B or whatever. Yeah, you could do sine of, I'll just go with my, well, yeah, you have to do C1 there. Okay, so sine of C1 over 5. Now, the reason why I'm doing C1 instead of putting 53.5 here is because I want to harken back to this. I want to use as much of this calculation as possible, okay? So that's equal to the sine of A1, which is going to be, 180 minus this minus 40. So it's going to be a little bit more information than 86.5, just to be clear, and that's supposed to be over lowercase a. I could do the cross product, solve for a, and I will get a equals 5 times sine of A1 over the sine of C1. Okay, which is approximately 6.211524847, right? But just, it's a length. So around to the nearest hundredth will be 6.21. Call it good. On your, oh, sorry, and just to be clear, this is lowercase a sub 1. This is still associated with case 1, okay? So there you have it. Now, case 2. Yep. Ooh, and I did not give myself enough room to do case 2 at all. LOL. Okay, so in that case, let me go ahead and do some on-the-fly adjustments here, which I'm sure is going to kind of flub things up a little bit here. Okay, but we're in case 2 now, where case 2. This is where your C2 value is equal to, we're going to round this to the nearest tenth. We'll get 166.5. or sorry, nope, that's not, hold up. Oh, sorry, that's not it. It's not this one. It's this one, 126.5. I'm looking at my notes and I'm like, why is this different than what I have over here? Nope, my C2 is 126.5 if I round that to the nearest tenth. Sorry for the confusion there, folks. 0.5, and it's in degrees. Box it up, call that one done. So the A value for that case, capital A sub 1, will be, you know, the 126.53. We'll add the 40 degrees to it. So we'll basically subtracting the 166.53, blah, 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 from 180, and we will get 13.5 when we round that to the nearest degree. Okay. And then you'll do your sine ratio proportion thing, law of sines, and I'll cut right to the chase and say, okay, lowercase a sub 2, therefore, and you could use the same kind of format here. You just change your subscripts of 1s to 2s. A sub 2 will therefore also equal 5 times the sine of capital A sub 2 over sine of C sub 2. And therefore that equals approximately 1.45. Okay. So there you go. 1, 2, 3, 4, 5, 6 answers needed for number 36 because we had 2 separate triangles to solve. Okay. So hopefully that landed really well, and we feel good about it. So I'm going to wrap up this lecture video. I know it's already quite long, but let's go ahead and do one what's it called, application exercise from this section. We could certainly do more in class if you'd like, figuring out the distances at sea in this particular lighthouse scenario. So we have the navigator of a ship at sea spots 2 lighthouses that she knows to be 3 miles apart. So there's lighthouse P and lighthouse Q, and they're 3 miles apart, as we can see in the figure. Cool. Along a straight seashore, sure. She determines that the angles formed between 2 line-of-sight observations of the lighthouses and the line from the ship directly to shore are 15 degrees and 35 degrees, as indicated here in the figure as well, right? We're going to, A, find out how far the ship is from lighthouse P, so that's this distance here, and how far is the ship from lighthouse Q, this other distance here. And then how far is the ship from the shore, so that's this dashed line distance as well, okay? There are a few things that I want to add to this figure to make it a little bit easier to work with, okay? So first of all, I'm gonna have this point here be labeled S for ship, okay? S. I'll put a big old S on top there. There's little fancy edges to it to make sure it's an S and not a 5. Okay, furthermore, I'm going to add, let's see, a little bit of information here. Notice there's a little box right here in this interior associated with this dashed edge, and there's an interior right triangle formed. 90 degrees are here, 15 degrees are here, so guess what? The measure of angle P is 75 degrees. It has to be in order for this little interior guy to be a triangle. We can say the same thing is true for this other right triangle that's happening here. 90 degrees there, 35 degrees here. How many degrees is angle Q, capital Q there? That'll be 55 degrees. So that's going to help us along in starting the process here for part A. So for part A, we essentially want to find the distance from P to S. Now P to S is opposite vertex Q, so I might call that length lowercase q, okay? Just to give it a name that upholds the convention that's already been put in here. So let's find Q. So I'm going to take what I fully know about What do I know? What do I know? Oh, I need to know the 3 miles side is opposite of a, how much is this whole angle right here? What's 15 plus 35? Well, that's 50 degrees for the whole thing, okay? So therefore, I can use the law of sines to say that the sine of 50 degrees over 3 is equal to, well, what angle is opposite this lowercase q edge? 55, right? That's the measure of angle, uppercase Q. So that'll be sine of 55 degrees is over Q, okay? Cross product solve for Q, and you will get Q is equal to 3 times the sine of 50 degrees over the sine of 55 degrees, which is approximately, taking what you get from the calculator here and rounding it to the nearest hundredth, you'll get 3.21. Slap some miles on it, and you are completely set for part 1. So just to be clear, the ship is 3.21 miles away from Lighthouse Q. Okay, how far away is the ship from Lighthouse, from Lighthouse P was part 1. It was the length of Q. Gosh, I'm making this more probably confusing than it needs to be. Okay, here we go. Just trying to uphold conventions here, guys. All right, so now we want to find the length from Q to S, aka lowercase p, if I'm upholding the convention. What is that length of the ship from Lighthouse Q? Well, that'll be set up in a similar way. Use that same known ratio of sine 50 degrees over 3 and set it equal to the sine of 75 degrees over P. Cross product solve for P. We'll get P equals 3 times the sine of 75 degrees over the sine of 50 degrees. Oh, you know what? I'm so sorry. I just realized that I had an error in my calculation, or what I wrote right here. I'm just like reviewing my notes. I am so sorry, guys. It's supposed to be the 55 degrees on top, 50 degrees on the bottom. Oh, my apologies for the confusion there. If you were doing the cross product there and then arriving at something different here and like being so upset and confused, I sincerely apologize. I wrote the wrong values there. Okay, so it's supposed to be 3 sine of 55 degrees over the sine of 50 degrees for part A, measuring the length of the distance from Lighthouse Q to the ship. Okay, cool. Sorry about that. But going back to part B here, where we're trying to find the length from the ship to Lighthouse Q, we have 3 times the sine of 75 degrees all over the sine of 50 degrees. Type that into your calculator, round to the nearest hundredth, and you will get 3.78 miles. Lastly, we're going to find the distance from the ship to the shore, so essentially this dashed line distance. And to do that, I think it's kind of best to just focus on this interior right triangle and kind of put in what we know to be true already. Well, we know that we have a 15-degree angle right here, and we have a length Q of what, 3, well, we don't even need that, do we? Sure we do, yeah. This 3.21, but you'll want to go back to using like the full value of it as much as you can, like as much as the calculator will give you. So I didn't bother with, in the interest of time, writing down the full expansion of this. I just wrote the truncated version for the final answer, but you'll want to harken back to that again. Use 3 times sine 55 degrees over sine 50 degrees. It's some decimal that goes on forever, but use as many significant figures as you can for Q. And then we're going to calculate the value. Let's go ahead and just call it X right here. Okay. And then that will allow us to, oh wait, do we need that? No, we don't. Sorry, not that one. I need to do a better job of looking at my X is the value that we want here, this dashed line. Okay, so we have the hypotenuse and we want to calculate the adjacent side, don't we? Okay, or if we want to, we could do the sine ratio, which I think is actually what I have in my notes. So we can use the fact that we have this 75 degrees right there. Cool, cool, cool. Which will be sine, in order to find the value of x, the sine of 75 degrees is the opposite side, x, over the hypotenuse of q, which is that value there. So if we just take q, it's rounded to 3.21, but use more information, times the sine of 75 degrees, and then round that to the nearest 100th rather, we'll get 3.10 miles, because the actual decimal expansion from the calculator is 3.0986718, blah, 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 blah. So round that to the nearest 100th. Even though the hundredths place is a 0, it's appropriate to have it presented as part of your final answer there, okay? And that's a wrap on law of sine. So we could do more word problems if it's relevant to the work you're doing for the homework. We can do whatever you want. And so look forward to entertaining cases 3 and 4 for solving oblique triangles in the form of law of cosines next time. Thank you so much for your attention. I'll see you soon.